In the next two sections, we're going to be interested in comparing samples from different populations. Let's assume that you have a sample of size n from a normal population with unknown mean mu1 and unknown variance sigma squared. And then you have another sample of the same size, also from a normal population with unknown mean mu2, which could be the same as mu1. They could all come from the same population, but that a priori might be different as well, and unknown variance sigma squared. And in both instances, the variance here is the same. These populations, though, are not independent of one another necessarily. It's possible that the two samples come from the same population or measurements on the same units at different times. People's height when they're 7 and when they're 20, right? You're measuring the same n people twice. So the measurement in the second population is not independent from the measurement in the first population. Tall kids at 7 are likely potentially to be tall adults at 20 and vice versa. Now we'd like to test for the null hypothesis that the underlying population mean is the same against the alternative that they're different, right? And so you can imagine a setup where you measure something, some quantity for n people, then you implement a change in policy. You wait a bit, and then you measure the same quantity again. And then you'd be interested in knowing if the mean value is the same prior to the policy change and after the policy change. So we do this by looking at the differences, the DI. So we pair the samples. We look at the second measurement on the ith observation and the first measurement on the ith observation. And we look at the difference. Now we could do x1i minus x2i or the other way around. Here I picked x1i minus x2i. We have to use a t-test because the variance, which is the same in both populations, is unknown to us. The test statistic in that case is a slightly different kind of statistic. D bar, the sample observed differences, minus the difference between the two means, but under h0 we're assuming they're the same, so this would go to 0. So this term here isn't going to be there, but it follows the same form as the t statistic for the previous test, divided by a sample standard deviation SD, I'll talk about this in a second, divided by the square root of n. So this thing has the same shape, the same form as the t statistic from the test for the population mean when we do not know the underlying variance. So it follows a student t distribution with n-1 degrees of freedom. That part's fine. The sample mean, d bar, that is just the average of all the differences. That part's fine. The SD would be, well, you need to think about it. It's the variance on the differences. And it's an estimate. We're estimating it from the data, so we lose 1 degree of freedom here. So 1 divided by n-1 rather than 1 divided by n, and then the sum of all of the square deviations, all the square differences, the observation of the difference minus the average difference, square that, add them all up, divide by n-1. There's your sample variance. Here's an example. You will test the knowledge of 10 engineers when it comes to basic statistical concepts. Before a short course in statistical quality control and after a short course. So we have 10 engineers. We give them a test before. Here are the grades on a scale of 0 to 100. And then we check their grades or evaluate them again after the course with an exam, and we check their grades again. The question is, will the course have been useful to help the engineers understand or better understand statistical concepts? So if you look at them one by one, like the first one had very little understanding, 43, then they went to 51. 82, 84, short increase. 77, 74, this one did not increase. 39, 48, that's a sizable increase. 51, 53, small increase. 66, 61, did not increase. 55.59 an increase, 61.75 increase, 79.82 increase, 43.48 increase. So amongst the 10, 8 of them showed an increase, but 2 of them showed a decrease. So if mu1 is the true population mean of the scores before they took the course, and mu2 is the true population mean of the scores after they've taken the course, what you are testing for here, assuming that these are normally distributed scores, then they might not be, but let's make that assumption. What you're testing for is that the null hypothesis is that the courses had no effect. The true population means would be exactly the same. Mu1 is equal to mu2 against the alternative hypothesis. What you're hoping to show is true is that the courses had an effect and it has increased or improved the engineer's basic understanding of statistical concepts, that mu1 is smaller than mu2. So this is a 2-sample paired test. For every observation, every unit, I have 2 measurements. And the 2 measurements refer to the same person, the same unit. You see they're not independent, right? If somebody had a decent understanding to start with, they kept their decent understanding. And if they didn't have that great of an understanding to start with, they didn't magically get like complete understanding. So the grades are linked, or they're in step. For the most part, some of them did see a pretty big jump. 61 to 75, that's a big jump. 66 to 61, that's also a big jump backwards. So you compute the differences for each of them. We do the first one minus the second one. We should mostly see negative numbers, except for those who did not see an improvement after the course. So what we get here. The observed sample mean of the differences is minus 3.9. On average, people's grades jump by about 4 marks. And the observed sample variance, which you compute directly, would be 31.21. The test statistic in this case would be the sample mean of the differences minus 0, assuming that the null hypothesis holds, which is to say that the population means are actually equal, divided by the sample standard deviation of the differences divided by the square root of the population size. And that should follow student t distribution with n-1 degrees of freedom if the null hypothesis is valid. The observed value of the t statistic, if you plug in the numbers minus 3.9, 31.21, and 10, will be minus 2.21. And now you compute the p-value that is associated with that. What's the probability that the sample mean of the differences would be smaller than minus 3.9? This quantity that you have observed. That would be the same as the probability that the student t distribution with 9 degrees of freedom, right? 10 minus 1, 9, would be smaller than the standardized coefficient here, which is observed to be minus 2.21. Or because the student t distribution is symmetrical, that is going to be the same as the probability that the student t distribution with 9 degrees of freedom would be greater than 2.21. The student t distribution, I'm talking about a random variable that follows a student t distribution with 9 degrees of freedom. You could compute this one directly using R or other software. If you're just going to use the tables, you need to make this transformation because the table gives you information about quantities that are computed this way. Even though in your case, specifically, you're sort of interested in what's happening here, right? That is not the way the tables give you the values. Now, the critical value of the student t distribution with 9 degrees of freedom at a value alpha of 5% is 1.833. And that's smaller than 2.21, which is the test statistic value, the one you've observed. And that's also smaller than the critical value of the t distribution with 9 degrees of freedom at 1% for alpha, 2.821. What it means is you can sandwich the observed test statistic between the 2 critical values at 5% and 1%. Let me draw this again so we have a good understanding of what I'm talking about. So this would be the T9 distribution. You have here, if you use 1.83, this is the critical point where this area under the curve is 5%. You have here at 2.821 the critical value where the rest of the area under the curve is 1%, and the one that you observed is 2.21. It's here somewhere. So your p-value is between 5% and 1%. The area underneath the curve of the t-distribution with 9 degrees of freedom from 2.21 onwards is going to be between 5% and 1%. So you would reject the null hypothesis if you need 5% certainty, if you're at the 5% level, but you would not be able to reject it at the 1% level, right? So at the 5% certainty level, confidence level, you would be able to say that the course has actually improved people's grades. At the 1% confidence level, you wouldn't be able to say that. You don't have enough evidence to say that. In the table, this is where you would find the values, right? You look for the numbers. You look for the degrees of freedom here, 9, and you look for the critical value for 5%, for 1%. This is the one you needed for the one-sided test that you had. The null hypothesis said that mu1 was equal to mu2, and the alternative hypothesis said that mu2 was greater than mu1, as opposed to not being equal to. That's a one-sided test. These are the values that you would use. Just make this visual a bit clearer than the one I drew previously. This is the one that you observed. This is the critical value at the 5% level. You are to the right of that. You are in the critical region, the rejection region at the 5% level, but you are not in the rejection region at the 1% level. Your evidence is strong enough for the 5% level to reject H null in favor of H1, but it is not strong enough for you to reject the null hypothesis at the 1% level.